Good afternoon, everyone. I'm Harshita Garg, and today I'll be presenting my work on a case study on long-term monitoring of repaired concrete in a bridge to assess its performance. It is co-supervised by Dr. Srijit Nanukotan from Queen's University, Belfast, Professor Anthony Conn and Professor Mohammed Bashir from University of Leeds. A brief overview about the bridge. It is built in 1932 in Northern Ireland using a Hanebic system for reinforced concrete structure. So overall, the structure was in good condition. However, with time, the concrete it started showing localized deterioration such as spalling and cracking of concrete while exposing the reinforcement of steel. In addition to that, there was a settlement of deck slab and cracking seen in the entire span of the expansion joint, leading to the reduction in the strength of the bridge. Therefore, this bridge was repaired and the major patches were filled with shrinkage-reduced flowable concrete. There was a waterproofing layer over the deck surface, while on all the exposed surfaces there was a water vapor transmissible membrane, which is a breathable coating layer to allow the water moisture to evaporate. So during the repairs, 3 septopods, there are 3 sensors that were installed to monitor the repaired concrete and to check whether this repaired concrete is working well or not, and to determine the rate of change of chloride ingress. So the review of sensors. So this is the expansion joint where the 3 sensors are installed. So these 3 sensors are a combination of corrosion sensors, electrical resistance sensors, and thermistors. So sensor 1 is located at 20 mm from the deck surface near the expansion joint, while sensor 3, which I'll be discussing here, is located at 20 mm from the soffit area near the expansion joint. Sensor 2 I won't be discussing in this presentation, just these 2 sensors. So these 2 sensors are oriented such a way to capture the changes in electrical resistivity and temperature near the deck surface and the soffit of the bridge. And the data was recorded for over 4 years, and it was recorded every 2 hours for 20 months. And thereafter, it was recorded twice a day for the remaining period. So this is the raw data that was being captured from the sensors. And you can see here that there were some missing information, some uncertain data, and some noisy data present. So with the amount of monitoring being done, the data collected is also accelerating. Therefore, it is making it difficult to analyze, manage this huge amount of uncertain sensor data, and it is time consuming as well. Therefore, an automated AI-based SHM methodology has been developed and applied to the data obtained from electrical resistance sensors, therefore to calculate diffusion coefficient to assess the performance of repaired concrete. So this methodology is a 5-step process where in the first step you gather the data from resistance data, temperature data, and all the ambient environmental conditions data. It is then pre-processed where you identify the missing information and the invalid data and clean it and use an Arrhenius relationship to correct the resistance for temperature to understand the effect of temperature and ambient conditions on the resistance measurements. Once the data is pre-processed, then you use a k-means clustering-based segmented regression, which provides us the insights on rate of change of resistance, stabilized resistance value, and time taken to stabilize the resistance, which then can be used to calculate diffusion coefficient values, and therefore that can be used in service life modeling for in-service performance. So as you can see in this raw data that there were huge cyclic variations in resistance for both the sensors, and this is majorly because the resistance is affected by the temperature measurements. With the increase in temperature, there was a decrease in the resistance. Therefore, this Arrhenius relationship is used to reduce the influence of temperature and standardize the measurements to 25 degrees Celsius. So these huge variations which were seen earlier, sorry, this is not moving. So the huge variations which were seen earlier now reduced, and we can see that even there is some missing information in the data, we can see overall the resistance is increasing with time. However, there is a drop in resistance around at the end of year 1. after the repairs. So this was because there was a leak in the repairs. So once these repairs were done again, the resistance started to increase. However, there was another increase in the resistance, which was around 600 to 700 days in between that. This was because there was a change in the frequency of data being captured. And secondly, the nearby areas of the bridge were heated up to get rid of the moisture inside. So that led to increase in the resistance. However, after that, after 700 days, there was a continuous increase in the resistance. So for further analysis, we are using the data after 700 days. So to assess this performance of repaired concrete, it is essential to discuss 4 parameters, that is, initial rate of increase in resistance, value of stabilized resistance, time taken to reach a stabilized resistance value, and value of diffusion coefficient, for which we are using here clustering-based segmented regression. So the first step is to use an elbow method, which is based on k-means clustering algorithm. In this method, so different values of k are run in the algorithm, and it identifies the optimal number of clusters using within sum of squares approach, and it shows that there are 3 clusters in the data set. To cross-validate it, we are using silhouette analysis, which identifies that how well each data points fit into a certain cluster. So and identifies how many optimal clusters are there. So in both the cases, we have seen that there are 3 clusters. So the segmented regression is done on 3 clusters such that it divides the entire data set based on the change in the slope difference. And the final intersection point of the 2 clusters is considered as the time taken to stabilize resistance and stabilize resistance value, while the 3 segments in each cluster shows the rate of change in the resistance. And it can be seen from the 3 regression values that in the final regression, the values are almost stabilized. So this approach was used on all depths for both the sensors, and the insights obtained from the data analysis are that the resistance was continuously increasing. However, there was a slow increase near the depth of the deck surface, while there was a faster rate of change and increase near the soffit area because of the maximum evaporation happening there because of the presence of breathable coating at the soffit. Secondly, it took more time to stabilize near the soffit, and it took almost same time to stabilize near the deck surface at both the locations. And the resistance values obtained also shows that the value of stabilized resistance is lowest at 20 mm from the deck surface, and it is increasing towards 70 mm from the deck surface, while it is the highest at 20 mm from the soffit area. This is because also of the surface releasing more moisture, because of the presence of breathable coating on the soffit area, while the deck surface has waterproofing layer, leading to slower resistance value. Therefore, these obtained values of stabilized resistance can now be used in the equation d by d naught is equal to rho by rho bulk, which is used to calculate diffusion coefficient, which can be used further for predicting the service life. So the values obtained for diffusion coefficient are lying in the range of 1 to 3 into 10 raised to power minus 12, implying that the repaired concrete is performing well. However, if the contamination has to arrive, then it may arrive in the bridge from the deck surface near the expansion joint, because this septopod one has more diffusion coefficient value. So finally, we can conclude that there is a continuous increase in resistance, implying that the repair area is still intact. There are no further issues that were observed from the sensors after the initial failure of the expansion joint. The values of diffusion coefficient are lying in the range of 1 to 3 into 10 raised to power minus 12. So the performance of the concrete is lying within the range of good quality concrete, implying repaired concrete is performing well and demonstrating the property to slow the corrosion process. And finally, it is recommended to use both relative humidity sensors and temperature sensors inside and outside the concrete to correct the resistance temperature measurements for relative humidity and to get better insights from the analysis for better decision making. Thank you. If you have any questions, I'm happy to answer.